Today on Under the Big Tree, it's time to observe our oscillations by building the JYETech DSO138 digital oscilloscope. DIY electronics is so much fun. It's really relaxing, you learn a lot, and it's a fantastic way to be able to add to your modular synthesizer for less money. Today, we're going to be building a kit that you can purchase from Amazon for about $45. It's the JYETech DSO138 digital oscilloscope. Digital oscilloscopes are absolutely fantastic. You can use them to be able to see exactly what's coming out of your synthesizer, and it's really helpful to be able to troubleshoot with when you're working on other DIY electronic circuits and things aren't going the way that you think they should. So you can take a look at this thing. It's the size of a module. It's not very big, it's not very heavy, it's not very expensive, and it's all you need to be able to look at what's coming out of your synthesizer. This episode is long, and I mean long. And at the same time, there was a lot of stuff that was out of focus, and the camera wasn't able to capture everything that I did, and so it's a little bit on the funky side. I definitely apologize for that. However, having said that, if you have never built a DIY module before, or if you've bought this DSO138 and you want to know how to put it together, then have I got the video for you. Come sit down and watch me go through the whole thing. We will sit there and identify all of the different components, look at soldering techniques, look at how to put them through the holes, how to be able to test it, test the voltage, be able to see it actually work, and then build this little acrylic box around it. So, having said that, if you're still here, then come on with me and let's go check it out. Okay, so here we are, and we're going to start putting together this DIY oscilloscope. I know that we're primarily focused on doing synth DIY, but there is no better way to be able to debug your audio circuits than to be able to have a visual representation of what you're seeing. So we're going to do this first. I bought this kit for about $45 from Amazon, and I liked it because it has the DSO138 oscilloscope with all of the instructions you can need to be able to build this thing bit by bit. And then it has all the rest of the parts as well. It doesn't just have the circuit boards. It comes with the mount to be able to have the different connectors to be able to plug into it. Comes with a power supply, a wall-wart power supply. And then it also comes with this nice acrylic plastic case. So we'll be able to build the case as well as everything else and have the whole thing as one all-in-one system. But the part that we're going to focus on right now is actually building the electronics. We have two packets of electronic components. We have the primary circuit board. You'll hear me call this a PCB board a lot. PCB board or circuit board. And then here is the little OLED display. This is the visual graphical display that we're going to be able to use to actually see what it is that we're looking at. One thing I want to show you about this, the parts are very small, but this is a relatively beginner's DIY project. And the reason that I say that is, if you take a look very closely, you'll see that it already comes with a whole bunch of components pre-soldered onto the board. So you can see here's a couple of integrated circuits and a voltage regulator, and there are some resistors there. Those components are super small. They're very, 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 very difficult to be able to solder by hand, but they're easy to be able to solder by a machine. And they are called surface mount components, or SMT. Typically, SMT components are done by a robot, although you can do it yourself. And the kind of DIY electronics we're going to be doing is called through-hole construction. It's the type of thing where we take these components that our hands can actually physically hold and be able to put them through the holes that you can see there all over the PCB board. So if you take a look really closely, you'll see, for example, C25. That's the name of a particular capacitor that we're going to plug in, and it's got
a circle to let you know that that's where it's supposed to go, and it has polarity, so it has a plus symbol near where it is that you're supposed to put the plus side of the capacitor. And there are a lot of things like that that will help you be able to plug the things in and be able to do it hopefully without making any mistakes. And here is the back side of the PCB. If we take a look at this, you can see that mostly all there is on here is holes that the through-hole construction goes through, and we turn it around to solder them on this side. So the first thing we're going to do before actually doing any soldering is organizing all of our parts. These parts are so small, and you don't get more than just what it is that comes with it. And so it's really important that you start by putting them in order so that it'll be really easy for you to be able to access them later. I don't have anything that's exactly right, but this will work. It's a little overkill. I have this gigantic 23-section storage case, which is way too big, but it doesn't matter. It'll get the job done. So the plan here, and the nice thing about it is when you stop working halfway through your project and leave, you leave everything in here, and then when you come back, it's all ready for you to start again. So we're going to take a look at all of these components here that we're going to need to be able to sort. And we're just going to open this up and pour them all into this very convenient little spot right there to be able to allow us to start sorting them. This is the BNC connector that our probe is going to attach to. And then we have some little plastic building materials and so forth. All very straightforward to organize. What's going to be a lot trickier, though, is organizing out these small components, which are really the meat of what it is that we're doing here. So we have these electrolytic capacitors. We want to look at them and make sure that the ones that are going in the same little pouch are all the same value. This one, for example, is 100 microfarads, 100 UF, and that one is 2. These are both 100 microfarad 16-volt electrolytic capacitors, so we can put them together into a box and we'll know that that's where they belong. There may or may not be other caps that look similar that are different values. The trickiest part for us is going to be identifying the different resistors. So these are a series of different resistors that we have, and a resistor is something that resists the flow of electricity. They're extremely common. They're used all the time in every DIY thing you can imagine. And if you look, they have sort of these little tiger stripes on them. And those aren't just for decoration. Those tiger stripes actually are color-coded and allow you to be able to visibly see what the color values are of these resistors by looking at it. But my eyes aren't that great, and I haven't done it that way for a long time. What I'm going to do instead, to make sure that we know exactly which the right ones are, is that I'm going to measure them using the multimeter instead. I'm going to measure the resistance of each of our resistors and put them in cases together with them, or just put them in little pouches together so that we absolutely know we're not putting the wrong resistor into the wrong spot. So let's take a quick look. So I'm going to turn on the multimeter. So we're going to take our ohm meter and we're going to put it maybe into the middle. We'll set it. It's got a bunch of, it has a series of scales, and so you use those scales to be able to zoom in and see what the particular resistance is of the value of your resistors, because there's an enormous breadth from, fractions of an ohm all the way up to hundreds of millions of an ohm. So we're going to take this now. Resistors are not polarity sensitive, so it doesn't matter which side we put the black and which side we put the white on. It does matter when it comes to capacitors, though. So take a look at this. It looks like we actually guessed right off the bat. So I set the scale to 200K or 200,000 ohms, and it looks like this is exactly a 200,000 or a 200K ohm resistor. We just happened to guess correctly. I'll move it up to here to 2 million, and we'll see that yes, indeed, it is in fact a 200k ohm resistor. If you go below it, so it's 200 kilohertz or 200 kilo ohms, and then I move the scale to 20 kilo ohms, then it just goes off the scale. It can't read it, and so it just comes up with a 1 there. And that's why we need to do the scaling. Okay, it's about 10 minutes later, and as you can see, I've organized all of the resistors. I've actually organized all of the components, and I'll show you the rest of them in the storage case after I get all the resistors done. There were so many of them that I thought I would take a little shortcut and just take a piece of paper, and as I measured the resistors, put them on the paper, writing down exactly what their value is. We're going to start setting these up, and I'm also going to show you what the naming conventions are for the values of the resistors. Okay, I wanted to take a little bit of a digression and talk about the nomenclature of resistors. Every time you work in some new field, of course, it's always got its own lingo. Electronics is certainly no different than any others. And so there are a few things you have to know about when we're talking about the value of resistors. So, resistors are measured in ohms. And resistors can have anything from 0 ohms, which is a straight wire, all the way up to hundreds of millions of ohms. So the symbol for an ohm that you will see attached to resistors often is the omega symbol, which is like that, the Greek omega. But in order to be able to make it easy for us to be able to see what the value is of a resistor at a glance, they have evolved a system that uses 3 letters, and those letters are R, K, and M. So M stands for millions, K stands for thousands, and R stands for ones. I don't know where it is that R comes from, but it's very useful. So I'm really glad that it's there. So for example, if we have a resistor that is 180 ohms, then you could read it as 180R, which is easy to see. If it's 180 kilo ohms or 180,000 ohms, then it's 180K. And if it's 180 mega ohms or 180 million ohms, that's right, you guessed it, it's 180M. As soon as you see those things with or without the little omega symbol next to them, you'll know what it is that they are talking about. So you can have this, but it is not necessary because the context of what it is that you're looking at tells you what it is that you're talking about. Now, there's one other piece of this that I really like as well, but it may look a little funny at first, so it's important to understand. And that is this. Let us say that we have something that is not an even number like that. Let's say that we have something that is 1,800 ohms. And we wanted to be able to display that in a little bit of shorthand. Well, 1,800 ohms is the same thing as 1.8K or 1.8 kilo ohms, and you may indeed see it like that, but there's another way of showing the same thing that I think is a lot easier and less ambiguous to see. And what that is that we take this letter here and we actually put it right in there where the decimal place is. So instead of saying 1.8K for 1.8 kilo ohms, which is correct, you can say 1K8, just like that. And it's one less thing to make a mistake on, and those periods can be a little bit difficult to see, so you don't have to worry about that. So I don't think I've ever seen this with Rs, but I see this with kilo ohms and mega ohms all the time. So 1K8, right? So 2.2 mega ohm, 2.2 mega ohm resistor would in the same way be listed as 2 M2 because the M has gone over there to replace the decimal point. So 2M, and that's a 2, not a Z. All right, let's get back to building an oscilloscope, shall we? Okay, we're going to start stuffing the resistors into the PCB. And the way that I like to do that is by using this trusty device here, which is called a Panavice. It's got these arms here to be able to hold my PCB board. So what I do is I take the PCB, move it over here, I adjust these arms till it's almost tight, and then when I flip this, boom, there's a little spring action, and it holds it in place just fine and quite gently. So what I'm going to do now is start stuffing some resistors. Now, fortunately for us, because this is sort of a beginner's kit, they give us a little checklist of the names of the different values of the resistors and the slots that they go in. So the 100K resistors go in R1, R14, and R16. So this becomes sort of a game of Where's Waldo a little bit, where we take a look on the board and we look for R1. Okay, so there's R14 right there, and we know that that's a 100K resistor. Now there's a couple of different ways to do this part. You can bend your resistor leads with a little plastic template that you can put it on, but for something like this I think it's easy enough just to bend them and put it in place. So I'm going to gently bend the leads a little bit like that, come over here to where it says R14 and put them through, drop it down. So everything is fine. Sometimes I bend the leads back in the back so there's no way that it can come out. So there's R14. Let's do the other 100Ks so that if we stop, we know where we are. So we're looking for R1 and R16. Okay, so I'm going to do the same thing. I'm going to stick R1 into the R1 slot. And the most important thing about this is that this is meant to be fun and it's meant to be relaxing. At least it's relaxing for me. And so I never am in a hurry, and I just go along and I double and triple check everything. And the result of that is that the most stressful and frustrating part of this, which is debugging, is left to a minimum. Doesn't mean there won't be any, but there'll be certainly less. So there's our 16. All right, and I'm going to do the same thing. Okay. There we go. All right, I want to make sure that the resistors are as flat as I can make them against the board. There we go. So now that I've finished those three, I'll just go right up here to my checklist and say, boom, you're done. Get out of here. So the rest of this is more of the same. So I'll shut off the camera now, and all I'm going to do is stuff all of the resistors into the board. I'm not going to solder anything yet, and then I'll turn the camera back on when we're ready to solder. Okay, we're back, and at this point I have now stuffed all of the resistors into the circuit board. As you can see, they are all as flat and tight as possible against the board, and everyone is painstakingly in the correct location where it should be. Let me show you what it looks like from the back. Here's the thing. So there are all of the leads in the back, and I've tilted them a little bit to be able to have gravity help hold them in place. I'm actually going to turn it over and just start soldering here on the table. And the reason is because that will allow me to be able to have the table push up and hold the resistors in place as we go. Okay, I've turned on the ventilation fan to be able to get the flux and solder residue into the fan and away from my lungs, which is a good thing, although it'll make it a little harder to speak over the noise. Basically, this is the way that it works. So you hold the PCB board, you heat the pad and the component lead, not the solder, and then you hold it in place until the solder wicks into the hole, creating a smooth and even cone. I'm going to do a couple more, and then I'll turn off the camera and continue this, and then we'll take it up after that. All right, all of the resistors have been soldered and clipped onto the PCB board. The first transport is away. Yay! So let's take a look here. Let's try to look from the side. As best I can do it. Hold on. There. As best you can see, unfortunately, you can see that all of the resistors are lying flat against the PCB. They're not absolutely perfect. Some of them are riding up a little bit on one side versus the other, but they're all flat against the board, and they are good enough for a homemade bit of DIY. The important thing is that none of them are touching, and as we look down at the board on the bottom side, it's really critical to see that none of the solder joints down there are touching. They're all relatively even. They all look relatively the same. They're all shiny, and they all, or nearly all of them, are a little volcanic sort of cone. Doing that ensures that we won't have cold solder joints, and it ensures that we don't have solder bridges or clumps of solder that go between different components on the bottom of the board, which cause things to short out. Okay, so here's the toolbox that I put the rest of the pieces in. It's too big, but it made it quick and easy for me to be able to sort the different components, which will make it much faster and less prone to error when I actually put the things into the PCB board. Okay, so the next thing on the list are a series of chokes or inductors. They look like resistors, but in this case they're a little bigger. And they are in the L1, L3, and L4 category. They've got a line with a little sort of double squiggle. So we'll put those in. Okay, check those off. Now the chokes are not polarity sensitive, but next up are the diodes, and they absolutely are. So if you put a diode in the wrong way, it will not work. So here is a diode, and I'm not sure if you can see in the camera, but there is a silver band on the right-hand side of the barrel there. You want to make sure whenever you're looking at an image of a diode that the silver band lines up with wherever it is that there's a small stripe there. The 5819 goes into the D1 slot. And then the other one is supposed to be a 4004 or 4007. So that one is going to go into the slot for D2, which is right there, and it says 14004 on it. So those two are done. And next up we have a crystal. Here is this little teeny tiny, this is the clock of our system. It's an 8 megahertz crystal. I think this is a good time to solder those units up, and then we'll go back to adding more parts. Oops. Okay, all of those components are in, and I've checked them. They're flat. So once again, we're going to take our pair of diagonal cutters and clip the leads down snug. Looks pretty good. So as you can see, we're building up more and more of the pieces. The diodes have the stripe matching the stripe. There is our oscillator, our crystal clock, and our inductors. So it's time to move on to see what's next. Okay, so this next part is going to be challenging. This is the USB port that's going to be connected to the circuit board right there. And you can see that is pretty challenging. Those little pads are very, very close together. This is almost, that stuff is almost surface mount level. So it's going to be a bit of a challenge, but you know, we love a challenge. So the first thing that we need to do is make absolutely sure that the pins themselves are aligned properly. I'm sorry for the bad camera work, but they're a little bit out, and so I'm going to take needle nose pliers and try to adjust them so that they all line up. That's better. I certainly have my magnifiers on, and now I'm going to try to line all of these up, and you'll know when it works because they'll all pop in place. Oh, just like that. All right, so let's take a look on the back. That's where it is, and you can make absolutely sure that all five of the leads are all going through the right place. These are all probably ground pins. These bigger ones, we're going to solder those in place, and then we'll have to go through and be very, very gentle and careful to get those 5 small pins without them touching each other. Now for stuff like this, just as a matter of course, I often just use the edge of my pliers to be able to hold this down and keep it in place. So by doing that, the unit that I'm trying to solder up is above the level of everything else, and so I can push down on it very gently with my fingers to hold it in place as I start to solder it up. Interesting. It's not wanting to affix to those tabs because they're all grounds, and therefore the heat is getting dispersed among the entire system. So we do have a solution for that. It's called a flux pen. Here's a flux pen, and this is merely used to put a little bit of the flux that's inside of the solder itself onto the PCB board to aid in the flowing of the solder. So I'm going to just dab a little bit on, and we're going to be cleaning all of the flux off of the board when we're done with some isopropyl alcohol, but I will bet you that's going to help move everything along. Okay, we've now managed to get the 4 pieces that are holding the USB thing in place, and we're just going to use a chem wipe to get rid of some of the excess flux that we ended up putting on the surface. Doesn't matter because we'll be cleaning that all up later with alcohol, but don't need to have any more on it than we need to. But that's now nice and tight. We're going to use a little bit more of the flux to paint the 5 pins that are really the business aspect of this whole thing. So much more gently than I did before. There we go. Just the smallest amount to help flow the solder. So the way that I'm going to do it, since I'm left-handed, I'm going to start with the bottom left pin, work my way up so that I'm not reheating any pins that I've already done, and then I'll turn the whole board around 180 degrees to try to get the rest of them. So when working particularly with really small things like this, it really pays to plan ahead. So here we go. We now have 5 of these little buttons that need to go onto the board. They're not polarity sensitive. They're a rectangle, and you can see down there the rectangles themselves. They have kinks in their leads so that they'll stay in place snugly once you put them in. And it's a matter of just working them gently in, and then they'll hold, and you can do all of them, you can solder all of them at the same time. There we go. There's the first one. All right, all 5 of them are now in. We can just turn this thing around, and there they are, all waiting to be soldered. And here we are with all 5 of the buttons soldered neatly to the PCB. Okay, the time has come to take a look at the weird nomenclature of capacitors. Like resistors, they have their own vocabulary and you just have to get used to it. It's not that bad though. The primary unit of measurement in a capacitor in terms of how much charge it holds is the farad. 1 farad would be written like that, 1F. Now, a farad is an absolutely gigantic amount of charge. We don't work with anything anywhere near that when we're working with electronics like this. Instead, we're working in terms of units like microfarads and picofarads. So, a microfarad is equal to 1/1,000,000th of a farad. So, microfarad. 1 of a farad. Similarly, a picofarad is 1/1,000,000th of a microfarad. Now, a microfarad is shown in terms of UF, and a picofarad is shown in terms of PF, just like that. You will see microfarads quite a bit in electrolytic capacitors. However, the really, really tiny capacitors that just hold a little bit of charge, like these tiny ceramic capacitors that we're about to put in, those are usually measured in terms of picofarads. Now, in order for them to be able to get all of these huge numbers onto these little teeny tiny ceramic casings, they had to come up with a system of nomenclature that is a little bit confusing, but it does work. Let's pretend we are trying to represent 33 picofarads. The way that this would work is that 33 picofarads would be represented as 330. So the first two numbers, the first two digits, are the primary value of the capacitor, and then the 0 over here, this digit right there, is how many zeros it's multiplied by. All right? What? So here's what I mean. So let's pretend that instead of seeing 330, this said 331. What that would mean would be that we would have 33 times 1 plus 10 equals 330 picofarads. If this was a 2, then it would be 33 times 1 plus 10, 2 zeros, equals 3,300 picofarads. Oh, and when you have teeny, teeny, tiny little things like 3 picofarads, they just mark it as 3. We now have this situation where we need to figure out what the values are of all of these ceramic capacitors that we have to put into our oscilloscope. And so, in order to make it easy, we're going to write down what those values are first. So we're going to have some that are 0.1 microfarads, some that are 330 picofarads, some that are 3 picofarads, some that are 1 picofarad, some that are 120 picofarads, and some that are 22 picofarads. So if this is the value, then what is the number that is listed on the ceramic capacitor? Well, 0.1 microfarads is number 104. So in other words, that's 1 times 10 times 1 with 4 zeros equals 1 times 1, 2, 3, 4. 10,000. So this is the same thing as 10,000 picofarads. 330 picofarads is the one that we showed before. It's 33 with a 1 because it's 33 times 10. Okay, 3 picofarads is 3, 1 picofarad is 1, 120 is 121. So we have 12 plus 1 0. 22 picofarads is going to be 2, 2, 0. In other words, no zeros that are, it's not multiplied by 10 or anything, and therefore it's just the 22 itself. If this is too difficult to remember, and goodness knows I barely remember it, just go to the internet and look for a capacitor number chart, and you will find all of this information. Okay, now after that exciting capacitor diversion, it's time to actually put the ceramic capacitors in where they belong. We have a whole bunch that are 0.1 microfarads, so we're going to save those for last, and we're going to do the other sort of the less common values here first so that we don't stand as much of a chance of making a mistake with them. And I'm going to pick up the first one, and the first one is 331, which is 330 picofarads, and that goes into C2. Now, one thing about ceramic caps is that they're not polarized, and you'll see that the symbol just looks like two little sort of backward T's back to back. The polarized caps, like the electrolytics, you'll see a little plus symbol or sometimes a little minus symbol next to one of the poles, reminding you that you have to put the cap in that way. Okay, now finally it's time to put in the 0.1 microfarad caps. These all say 104 on them. And fortunately, they're a little bit bigger than those other ones, so they're a little bit easier for my big hands to handle. So there are 11 of these. They go into C1. They basically go into all of the slots that are left for ceramic capacitors. So there's C1. I'm going to turn off the camera, put these ceramic caps in, and solder them in the back. It's exactly the same as all the other components we've been soldering, and then I'll be right back. All right, well, we are done getting the ceramic caps on. You can see they give a little bit of depth to our little oscilloscope valley here. It's looking pretty good. All of the connections on the back look pretty clean and pretty solid. I don't see anything bad, any solder bridges or anything like that yet. And so it's time to move on and start putting more of the components on. Okay, we're going to put in a few one-offs right now. The first thing we're going to put in is the single LED that's on the board. Like the other kinds of diodes, an LED or light emitting diode is definitely polar. In this case, with an LED, you can always tell the positive side is the one in which the leg is a little bit longer. It sometimes has a flattened area on the same side of the physical LED casing. And if we look down here at where the LED is supposed to go, the positive side pad is square and the negative is circular. So there's 2 or 3 different ways we can tell the right way to be able to line up our LED. If we put it in backwards, that'll be the end of that LED. There's the LED. Now we have a little power coupler. This is supposed to be put in with the facing outward. And if you take a look here closely, you can sort of see that there's a stripe there that helps you line it up with the way that it actually physically is supposed to be in there. So in that goes. And then we have 2 of these capacitor trimmers, which are also strange, fairly uncommon little devices. If you can look and see, there's a flat side and a circular side. And if we look here about where they're supposed to go on the board, we can see that there's a flat side and a circular side. So they're telling us the right way they want those guys in. Okay, now it's time to put in all the electrolytic capacitors. So just like the LED, the light emitting diode, these capacitors, the longer end lead is positive. And also with these, you can see the negative side has got a little stripe with a negative on it. So if we go over here and take a look at C24, for example, we can see a square pad with a plus. And so that's where the positive side of the cap goes. Okay, I'm going to finish these up, solder them up, and I'll be right back. All right. Well, all of those components have gotten onto our ever-expanding oscillator board here. Lots and lots of holes have been filled in. The one thing I wanted to show you right here. Oh no. Let's see if the camera can show that. It is a solder blob. So that is a place where I got too much solder on it and the two leads are connected together, which will not work. So I'm going to show you how we get rid of that. There are a number of different things we can use. We can use solder braid, which is one good way to do it. That's a good way to sort of sop up a bunch of solder. And we can use our solder sucker, our vacuum pump. I think for this, I'm going to try using the solder sucker. The other way, when you're working with surface mount, particularly components, you can also just get in there with the soldering iron in between where the solder braid is and just sort of flick it out of the way. You just sort of deftly get in there and flick. So I'm gonna blob it up again so that I can use the solder sucker. Come on. Blop. Okay, there we go. Darn it. Being so efficient. All right, now we're going to try doing the same thing with the solder sucker. I'm going to put the solder sucker right there on that side, and then come in here and heat it up on this side. And once it's done, all there is to it. So that took off the solder bridge, but it also took out some of the solder that was being used to hold a good joint for that one lead there, so I'm going to resolder it. There we go. Solder bridge fixed. All right, we are now in the home stretch as far as the passive components go in terms of building our oscilloscope. The last four things that we need to add are right here in my hand. These are transistors and voltage regulators. So the tricky thing about transistors is that they all look exactly the same. They're, you know, a little black piece, a little black half moon piece with three legs. There's only one way that they go in, of course. The polarity is really important. They all look the same, and the only thing that's different is some very faint writing on the flat side of the transistor. So in the case of this particular build, there are two transistors and two voltage regulators, all of which are different and all of which look exactly the same. And so we have to be triply careful to make sure to put the right ones in the right spots. So let's start with the first transistor. So if you take a look here, you can see the organization, the way that you should actually put the thing in. And basically a transistor is an amplifier very much like the vacuum tube before it, but it's a whole lot smaller and uses up a whole lot less power. There's the collector, the base, and the emitter. The idea is that there's voltage coming in, voltage coming out, and a control signal that tells you how far to open the spigot. There we go. Super useful, of course. And transistors are still in use, even though integrated circuits are much smaller and much more efficient in terms of jamming a whole lot of them on there at the same time. Now, the one thing about transistors is you really want to be quick about soldering them. You don't want to hang out applying heat to the legs for too long, because you could potentially damage the transistor. I've never done it, but I'm sure you can. At least I've never knowingly done it. So the more I work on this design, the more I realize just how flexible and well designed it really is. For example, here is the power section of the board. It has both a header for a DC 9-volt system, but it also comes with an AC adapter and this power header right here. So we are going to attach that there. And then we will have multiple different ways of powering this bad boy. Next, we have some pin headers to put in. Now these, they come in a long strip like this, and what we need are 3 of them to go into that hole and 4 of them to go into that hole. So all you do is you take your diagonal cutters and you say, all right, well, I want 3. 1, 2, 3. Make sure that you're not pinching anything. Give it a little snip. And there are our 3. Now we'll do the same thing with the 4-pin header there. And this time we have 4 pins. Stick it in. Okay, next up are these female headers that we need to add. There are 2 of these little teeny 2-pin female headers. They just fit right in to the board like that. Then the last one is this gargantuan pin header, this 20-pin header here that is going to be connected to the display. So the male pins are in there at the same time. So we're going to pull those out just to make darn sure that we solder it the right way in. Very gently disconnect. Back and forth. The last thing we want to do is have to go to the electronics store. I can just very gently push up on the pins all the way around and be able to disconnect it. Anything, there we go. Okay, so this is the male header piece that's going to go on the monitor, on the LED display, and this is the female piece that's going to go right there. So the first thing we need to do is look for any bent pins and adjust them into place. And there's one right there, right at the edge. We need to bend those back so that everything is square so we can get it in. Now what we do, or what I do once we get it in, there. We're going to put it down, and I am going to solder 1 pin on each corner. And the reason is because that gives me the ability to make sure that it is flat and tight against the board. So I'll start with this pin. You have to make sure that's the case before you start soldering a bunch of pins, because if something's wrong and needs adjustment and you've already soldered 8 pins down, then you're out of luck. All right, so that was our first corner. And I take a look very carefully and I can see that it's pretty flush. Now, I've soldered that corner and that corner. And I can look up here and see that it is perfectly flat against the board. It's just right. And so now we're ready to go and solder all the individual little pins. Now, this is obviously a place where solder bridges can get involved if you're not careful, and so you have to make sure they don't. As I said, the technique that I like to use is this. So I'm left-handed, so therefore I go here to the left side, and I'm going to start right here between these 2 pins on the bottom. And the reason is because I don't care if I hit this pin with the soldering iron. I'm soldering this one. If this one already had solder on it, then I could make a mess and cause a blob of solder and so forth. But because I do it this way, I can just solder them 1 pin at a time. And work my way up. So now the one that I soldered is not being touched by the soldering iron. So I can just solder the next one and continue. Just like that. Now, So now you can see that I've done about the first 4 or so. I'll finish those up. When I'm done, I will physically turn the board around this way and do exactly the same thing going in that direction. So whether you're left or right-handed, this technique is a really good way of being able to solder all these little tiny pins together with minimizing the amount of time that you can spend accidentally resoldering or heating up something that you've already soldered. So I'm going to turn off the camera, do that offline, and I'll see you in a minute. Okay, 40 solder joints later, we are done. You really get into a flow with this stuff, pardon the pun, once you get into it, and I was able to get them all done. Every one of them is neat and clean. No solder is bridging from one to another. They all have that nice little sort of conical blob. And this is completely tight. So the next thing, and we really are coming towards the end of this part, is putting these switches here on. So these switches are polarized. So once again, I'm going to take a look at this guy before we try to put it on and see if there are any bent pins, which there are. And so rather than trying to fix it later, I gently bend it back into shape and then take this and gently try to get all of the pins onto the PCB board so they all line up. There's nothing worse than putting it in and pushing it and bending a pin that wasn't actually ready to go. But in this case, it looks like they're all there. And so I can gently push both sides of the switch into place, and it fits like a glove. Without even soldering, it makes a really good, strong connection. Okay, all 3 of them are now connected, and now all I have to do is solder them, just like everything else that we've done, same technique. All right, well, all of those got soldered. Everything is good. We are now to the last task on page 1, woohoo, which is attach this BNC connector in. This is going to be the device that the probe connects up to, and it's really thick metal. And it says here, note the thicker pins need to heat up longer to get good soldering result. So agreed, but we will also take out our friend, the flux pen, and get a little flux going on there to be able to help convince those thicker pins that they need to be soldered. Now I push the BNC connector down really strongly onto the thing so that there's some physical connection as well, because this is going to get connected and disconnected a lot, and so we certainly want to make sure that it is really, really strong, as strong a connection as it can possibly be. So we'll start with the thinner of the thick pins. Yep, that's good. I can see that there's solder all the way through and up on the other side, so that one's good. Now we have these 2 thick metal ones that are connected to the outside of the BNC connector, so I am just going to be very patient and sit there and just wait for a few minutes, well, for a few seconds anyway, for the pin to heat up and see where we go. I think I'm going to turn up the temperature temporarily and see if we can use that to convince this pesky BNC connector to be our friend. Now we got it. So take a look here. We can see that it's got 2 nice big solid shiny connections, so that BNC connector is not going anywhere. Wow. And that's the end of page 1. That is looking like one mighty fine and mighty busy piece of circuit board there. So let's go over to page 2. There are only a few things before we are actually ready to begin testing. So we are going to take one of our leads. This is going to be a test lead. Make a small ring with it. And then we are going to connect it in to J2. Then it says to short jumper 3 with solder. There is jumper 3. So if we take a look right there, there's that little surface mount pad. It's already got a little solder on it, and they want us to just jump that, purposely create a solder bridge to make a permanent connection there. Now we have to put the connections onto the back of the LCD board. So we've got a header connection with, I believe, 40 pins that has to go right there, and then a couple of 2-pin connections that go there and there. And those things are what we're going to use to connect the LCD board to the oscilloscope, just like that. The first thing we're going to do is do the big, long, complicated one. It's in, and it's completely tight. I'm going to hold this down here. And just like on the other ones, I'm just going to solder down one end on each side, one corner on each side, and make sure that the connection is really good, and then I'll go through and solder the rest of it up. There's our first one. So then I'll do the other one kitty corner to it. There we go. So now we're going to do these in order. And I'm going to start with the inside because that looks like it's going to be harder to gain access to. So you think ahead. If I take the soldering iron and I go this way, then it doesn't matter whether I heat this pin again or not because it isn't soldered yet. And so I'm not going to have to worry about creating solder bridges or anything like that. So I'm just going to start here and work my way up. All right. That looks really clean. No solder bridges. Everything is a sort of the well-formed volcano, except maybe this one. Looks really good. Okay, now I'm going to start the outside series. Okay, now we have these two little jacks that we have to put in on the other side of the board, right there and there. They give us 4 of them, so we're going to use our diagonal cutters very carefully to clip right in the middle between them. All right, this should be a piece of cake. All right, that is it for the soldering for right now. And now it's time for us to check the voltages on the main board and see how it is. We're going to check to see if the initial voltage is correct. We're going to do that by taking this 9-volt power adapter, plugging it in. All right, so now 9 volts of power is coming into the board. And then we're going to take our probes from our multimeter, which I currently have set to checking for DC voltage, which is what we want, and it's set at a maximum of 20 volts. We know that we're going to be looking less than that, so that scale is good. We're going to take the black and attach it to the ground point that they have right there, and then they have a little point here that says plus 3.3 volts, and we're supposed to attach red to that to see. And as we can see on the multimeter, we've got 3.29 volts. So I'm going to call that a win. Now, the next thing we have to do, once that's done, is there's a little teeny tiny solder pad there, JP4, that we're supposed to solder together. I presume that'll bring some other voltages in line. We will find out. There we go. All right, next step is to attach this board. Time to attach the TFT board. Put it all together. Make sure that all of everything is in place where it should be. And it all fits like a glove. We have a little sandwich there. And it all worked out. Now comes the scary part. Let's see if it turns on. Look at that. So it all looks like it all worked. Incredible. So now with all those basics in place, let's attach the probe, which is a single BNC connection. Okay, let's see if we can see anything. Okay, so the moment has arrived. Here we are. You can see that I've got a plug plugged into my STO oscillator. And we're going to follow it down to here, where it connects up to the probe, which then goes into the oscilloscope, and then shows us that. Woohoo! So it does appear to be working. I'm going to adjust the frequency on the oscillator, and look at that, just like you'd expect. As I turn it slower and faster, the waveform changes appropriately. Let's try plugging it into a different wave shape. There we go. Completely different looking wave shape. And let's go over here to there we go. Here is a depth for a VCO. We're plugging into the sawtooth. And as I tweak the tuning, it changes it a little bit. And of course, as I change the range of the tuning, it'll change quite a bit. Cleanly, here's a triangle wave and a sine wave. And look how different the sine wave looks coming from the depther than from the STO. Totally different looking sine wave. But the good news along these lines is that it all works, and hooray! Now all I have to do is build the box for it and I'll be all done. Okay, the last stop on our little train ride of oscilloscope building is to create the box, the casing that the thing comes in. The version that I bought came with the casing, but I managed to break it to the point where it made more sense to buy another one. And since they were only about $8, it's not a big deal. There are these sort of neat acrylic clear cases, but you know, when they say acrylic, I had visions of bulletproof plastic, and what they really meant by that was clear plastic. So there are a couple of engineering faults in it that you have to be very careful about when you're actually building it, or you'll be buying another one, like I did. Specifically, right here. That and that are 2 points where it's extremely easy for them to snap like a twig, and then you have to do it again. So we have a whole series of bizarrely shaped pieces, all of which have got this this paper on it. And so the first thing that you have to do is go through and remove the sticky paper from both sides, which takes a little bit of time. Then you have to put it together. The shapes are so weird and it's so unintuitive that there's no way you can do it without the instructions. But fortunately, the instructions are available on the web, and so it's really pretty clear how to actually do it. So I'm going to shut off the camera and take all of this paper off, and then we'll be right back. Okay, that highly tedious job of peeling off all of the paper is now done. So we have these weirdly shaped pieces of plastic. So let me show you basically how it works. The thing that you start with is the TFT screen, which connects up to this piece here. And you have to make sure that you do it in the right orientation for the buttons and sliders to be able to connect up to that the way that they should. And even that's backwards. There's only one proper orientation. Here it is. So you set that up to make sure that everything lines up properly. And then you're going to put that on there. We're going to start by screwing this piece onto there, and then we attach these plastic, basically switch and button extenders into these slots. So these things are going to go on top of each of those, and these pieces here are going to go on top of each of the buttons. And so that all happens. Then once we put these sliders on, then we put on 2 layers of this thicker of this other piece of acrylic, again with everything lining up properly. 2 layers basically just to make it thicker, I think is what they designed. And then finally, there's one more piece of solid plastic that goes over the whole thing, and that completely covers the TFT slide piece. Then finally, you put these 4 pieces all the way around the sides, and then here's a piece for the bottom, and then you're all done. So let's get started. Okay, so we get started by confirming for the 14th time that the orientation of this piece of plastic is correct with the oscilloscope main CPU, the main PCB. And once we're sure of that, we use these teeny tiny little M2 screws to be able to attach the TFT directly to this board. Okay, I finished getting the screws in, and then I used a little microfiber cloth to wipe the top of the TFT screen because, of course, there's, oil and fingerprints and stuff like that. And so you want it to be as clean as possible. So then I'm taking these 3 sliders and putting them in there, and then these 5 button extensions and putting them in there like that. 4, 5. Okay. Now we put these pieces on top, making sure that everything, all of the other cuts are lined up, which they are. And then we do the same thing with the second one. Here we go. And so then we take this top protective plate and we do the same thing. And there we go. Again, there's only one orientation that works. So save yourself some time and hassle by getting that right. So that all looks good. So now that that's in place, we get to take this whole sandwich and attach it to the CPU, the PCB board. So very carefully, making sure that all the pins go in the right holes. Okay, so I've made sure that all of the sliders are connected to the switches and that all of these things are in their proper location and all of the pins are right. So then I can push it down and perfect. And we've got ourselves a little acrylic sandwich. So now that we have this, gently go get these long screws here and run them through. And there's going to be more of the screw sticking out the bottom because we've got these nuts and then we've got these end caps. And the nuts are to finish putting this sandwich layer together, and then the end caps are going to be when we put the rest of the box around it. And I'm not going to bolt these in too tight because if I do, then it's going to start squeezing and putting pressure on the circuit board at the edges, and we don't want that because that could eventually result in broken solder joints and general mayhem. Okay, I've got them all on. I'm just going to do one gentle tighten of each one. Just want it on there until I don't feel any pressure, or until I don't feel any looseness, but no tighter than that. So there we have the primary, piece of our whole thing. Then we're going to attach the other 4 sides and then the bottom, and then we're done. Okay, I made one little mistake that requires a small tweak. which is namely that this side piece, you need to have a little bit of play to be able to get it in there, otherwise it won't fit, and so you can't do it while while everything is tightened down. So I pulled the bolts out just a little bit, just about halfway, to give me a little bit of room so that I can then take this piece of acrylic and slip it in and have it fit over the BNC connector. All right, so once that's done, then you can tighten these down again because the rest of the sides just slip in place. So I'm going to do, again, just a very gentle tighten of the bolts. Tightening of the bolts. Yep, still work. If you tighten it too much, the buttons will be crushed against the button tops will be crushed against the buttons, and then they won't be able to work. They won't be able to push down. Okay, everything is in place. That's connected. I've confirmed that these switch tops are still connected to the switches because it's easy for them to be able to fall out of alignment. And now we just put the rest of the pieces in like a little log cabin. Okay, so now all 4 of the sides are in. There's the USB port is available. Those things are connected the right way, so we know that we have the orientation of this whole thing correct. Now we take the bottom. Nope. This way. And gently put it in place. And it all fits together like a nice Dagwood sandwich. So at this point, all we have to do is screw these end bolts on. I want to make sure. Yep. We screw these 4 end bolts on and we're done. And we're done. All right, let's take it upstairs and plug it in and make sure that it still can read what our synthesizers are telling it, and then we'll be all finished. Okay, and now finally, it's time to test this bad boy out. So here we have the oscilloscope. I'm going to take that off. So I'm going to take the oscilloscope, it's plugged in over here with power, and then I'm going to take the BNC connector, attach it up, and then I've got the connections going to the tip and the sleeve of this regular old 3.5 millimeter cable, and let's plug it in to the, and let's plug it into the STO. Let's reboot the thing. Okay, it's up and running. Whoa, look at that, a sine wave. And as we change the frequency, we get exactly what we would expect. I'm going to pull it out, stick it into this other one. Ooh, look at that interesting waveform. So you couldn't ask for better. This is absolutely perfect. It's exactly the right size to be able to use for troubleshooting your synthesizers and stuff. It's tiny, it's cheap. What's not to like?
Well, thanks a lot for watching through all of that. I really appreciate it. I hope that you learned something and that you're excited about building your own digital oscilloscope and you feel empowered to be able to build your own stuff. That's it for this episode of Under the Big Tree. As always, if you like what we're doing, please feel free to like, share, and subscribe. For now, this is Nick, signing off.